Basic concepts of a PN junction, intended for third semester or second year UG Electronics Engineering students. The prerequisites. To understand this presentation, you should have the following prior knowledge: conductor, insulator and semiconductor, and resistance or conductance of each, some commonly used semiconductor materials, the basic atomic structure of semiconductor material, doping and the types of semiconductor material formed with doping, the current carriers in N and P-type material, current flow in semiconductor material. Student learning outcomes. Upon completion of viewing this video, you should be able to explain the formation of a depletion layer at a PN junction, discuss the flow of current when the PN junction diode is forward biased, discuss the flow of current when the PN junction diode is reverse biased, and discuss the IV characteristics of the PN junction diode. What is a PN junction? When a P-type material is joined together with an N-type semiconductor, a PN junction is formed. It is also known as semiconductor diode. Diode means a device with two electrodes, one positive electrode anode and a negative electrode cathode. Semiconductor diodes are widely used in electronics industry. One of the most important applications being rectifiers, which converts input AC signal into DC output signal. Now we come to the diagrammatic representation of a PN junction. Here we see that P-type material is on the left while N-type on the right. The majority carriers of P-type holes are shown in white circles, and the majority carriers of N-type electrons are shown in blue circles. Now when these two types of materials are joined, the physical contact area is known as the junction. The majority carriers have a stark carrier gradient, that is, the concentration differs greatly from region to region. On one side, holes have a majority concentration while they have a very low concentration in the N side. Similarly, electrons on N side have very high concentration on N side and very low concentration on P side. Hence, what occurs is diffusion. We know that diffusion is the process of flow of particles from regions of higher concentration to regions of lower concentration. Now, the majority carriers of P-type, that is holes, cross the junction and recombine with the immediate atoms near the junction to form ionized donors. Similarly, the electrons cross the junction and recombine with the immediate atoms near the junction to form ionized acceptors. These ionized acceptors and donors build up an electric field, which further stops the diffusion process. The ionized acceptors repel any electron that try to cross the junction from inside. Similarly, the ionized donors repel all holes that try to cross the junction from P side. The extent to which the ionized acceptors and ionized donors exist around the junction is known as the space charge region or depletion region. When we see the electrostatic potentials of P-type and N-type material, there is a huge difference between the two materials with respect to the electrostatic potential. This is known as the potential barrier height or contact potential V0. So what we discussed can be summarized as: the diffusing majority carriers from the two regions recombine near the junction and disappear. The uncompensated acceptor and donor ions set up an electric field which halts majority carrier diffusion and causes minority carrier drift. The two kinds of majority carriers diffusing across the junction meet each other near the junction and undergo recombinations, leaving negative ions on the P side and positive ions on the N side of the junction. The distribution of positive and negative charges is called space charge, hence the name space charge region. The same region is depleted of any mobile carrier, hence it is called depletion region. It has a thickness of 0.5 to 1 micrometer. The diffusion of electrons and holes stop due to the barrier potential difference or the potential difference across the junction reaching some critical value. The barrier potential difference or the contact potential depends on the type of semiconductor, temperature, and doping densities. At room temperature, the typical values of contact potential for germanium, it is 0.2 to 0.4 volts, and for silicon it is 0.6 to 0.8 volts. The standard circuit symbols of diode, usually the second one is prevalent, where a triangle and a line on the apex of the triangle represent a diode. The base of the triangle forms the anode, that is the positive terminal, and the line on the apex of the triangle represents the cathode, that is negative terminal. When we draw the energy level diagram of a PN junction with P on the left side and N on the right side, we see that the energy level of P side is higher than energy level of N side. EV represents the valence band edge, EC represents the conduction band edge, EF is the Fermi level, P on P side, and EFN, that is the Fermi level on N side. We see that on P side, there is the majority of holes in the valence band with few free electrons in the conduction band, while on N side, very few holes in the valence band and high density of electrons, free electrons in the conduction band. The difference in the energy of P and N side can be given by E times VB. E being the electronic charge and VB is the contact potential. Now we come to biasing a diode, that is applying an external voltage to a diode. It can be done in two ways, one forward bias and another reverse bias. When positive terminal of the battery is connected to the P-type and negative terminal is connected to the N-type of the PN junction diode, it is said to be a forward bias. When negative terminal of the battery is connected to the P-type and positive terminal is connected to the N-type of the PN junction diode, it is said to be a reverse bias. Now let us consider one at a time. First, forward bias. We have a PN junction with no external bias and a PN junction with forward bias. Forward bias means P-type material connected to the positive terminal of the battery, N-type connected to the negative terminal of the battery. We observe that the majority carriers of P-type, that is holes, are repelled by the positive terminal of the battery towards the junction. Similarly, electrons are repelled by the negative terminal towards the junction. Hence, both the majority carriers are pushed towards the junction. If the applied voltage is increased, the space charge region will get narrower and eventually will collapse, and there will be free flow of current across the junction. Hence, the barrier potential difference is decreased by the external applied voltage. The depletion band narrows, which urges majority carriers to flow across the junction. A forward bias diode has a very low resistance. So we can say that under forward voltage, a PN junction has large current across the junction. Now we come to the reverse bias condition. Reverse bias means P side connected to the negative terminal of the battery, N side connected to the positive terminal of the battery. We observe that the majority carriers of P-type holes are pulled towards the negative terminal of the battery away from the junction. Similarly, electrons from N side are pulled away from the junction towards the positive terminal of the battery. Hence, the space charge region widens. The barrier potential difference increases under reverse bias. The depletion band widens, preventing the movement of majority carriers across the junction. A reverse bias diode has a very high resistance. So we can say that under reverse voltage, a PN junction conducts very small current. Other points that should be kept in mind under reverse bias are only thermally generated minority carriers are urged across the PN junction. Therefore, the magnitude of the reverse saturation current or reverse leakage current depends on the temperature of the semiconductor. When the PN junction is reverse biased, the width of the depletion layer increases. However, if the reverse voltage gets too large, a phenomenon known as diode breakdown occurs. Now we come to the VI characteristics of a PN junction. Graphical plot of the applied voltage V against the current across the junction I is known as the VI characteristics of a PN junction. we can see that the forward bias conditions or the forward bias characteristics can be represented by the first quadrant, and the reverse bias characteristics are represented in the third quadrant. Forward bias voltage is considered to be in the positive x direction, and the current that flows is from p type to n type under forward bias, so it is in the positive y direction. Similarly, the applied bias under reverse bias is opposite to that of forward bias, so it is in the negative x direction, and the current that flows under reverse bias condition is due to the minority carriers that flow from n side to p side, so it exists in the negative y direction. Two other points that should be kept in mind while we draw the VI characteristics are, first, knee voltage or cut-in voltage, that is the voltage at which the current increases appreciably from 0. And the second one is the reverse breakdown voltage, that is the voltage at which the current rises sharply under reverse bias with almost no increase in the applied voltage. The description included: when the diode is forward biased, the current increases exponentially with voltage except for a small range close to the origin. When the diode is reverse biased, the reverse current is constant and independent of the applied reverse bias. Turn on or cut in or threshold voltage for a forward biased diode is the voltage when the current increases appreciably from 0, and it is equal to the barrier potential difference. For germanium, it is 0.2 to 0.4 volts at room temperature, and for silicon it is 0.6 to 0.8 volts at room temperature. From the graph, the following points are noted. The region between knee voltage and breakdown voltage is known as the non-ohmic region. Above the knee and the breakdown voltage, the current increases. Breakdown voltage is due to thermally broken covalent bonds. And finally, diode is conducting in forward bias and non-conducting in reverse bias. This completes our discussion on the basic concepts of PN junction. Thank you.